In the last lesson, we introduced the concept of machine learning and distinguished between supervised and unsupervised learning. We mentioned that in supervised learning, the learner is trained and makes use of data sets associated with labeled features, which define the meaning of our data. That way, when it's introduced to newly inputted data, it's able to predict missing information based on established rule sets and patterns. In other words, in supervised learning, a learner is provided examples of certain inputs and outputs, and based on that training, given a new input, it's able to predict the corresponding outputs. In this lesson, we'll talk about linear regression, a supervised learning algorithm that allows us to make predictions based on linearly arranged datasets. For now, we'll look into an example of a simple linear regression model, which would model the relationship of a quantitative response variable and an explanatory variable. The response variable is the dependent variable whose value we want to explain and predict based on the values of the independent variable. More specifically, we'll look to establish a linear relationship between the price of the house with respect to its size. The price of the house will be dependent on the size, and as such, it will represent our response variable, whereas the size of the house is the independent variable whose values we're going to use to try and make predictions about the price. Accordingly, the size of the house is the input, and the output is what we're trying to predict, the price itself. We're currently given a set of data points which reflect the price of some houses based on their size, and for each house with a given size, it's given a price label. This small 400 square foot house is $210,000, and the larger 600 square foot house is about $480,000. What about the value of the 500 square foot house? Well, you could just eyeball it and estimate that it's somewhere over here, or even do some kind of interpolation to get the exact value, or we can draw the line that best fits our data. We're applying a linear function that best approximates the relationship between our two variables. This creates a predictive model for our data, showing trends in our data and can thereby predict values of new data, which were not initially labeled. This is known as linear regression. Thanks to the linear function that we established from our previously labeled data sets, if we're given new inputs, which don't have a label, we're able to predict and estimate the output based on where the y value falls on the regression line. That's one form of supervised learning, predicting the values of new data based on a linear regression, and it's important to note that realistically, data does not behave like a straight line. They are random x and y observations that on average may follow a linear pattern, which is why we use linear regression models to represent them. As such, the linear regression model also accounts for an error value. Our predictive model, through some learning rates, learns to minimize this error by updating its linear function until no further improvement is possible. Thanks to this linear function that we established from our labeled data sets, when we're given new inputs which don't have an output, it's able to predict the most accurate value based on where its value falls on the regression line. Linear regression is one of the most well-known and understood algorithms in machine learning. This actually segues into our next discussion, where we'll also learn how we can use lines to classify data among discrete classes. This is another form of supervised learning called classification, a very important concept in self-driving cars.